Finally, let's talk about Layer 3 VLAN. The following configuration does not need to be changed. I just stop this device. Then turn it back on. For this device, just wait and reconfigure access. You can imagine that there is a virtual router in the switch. The router has its own interface. This interface can be configured with IP. I'm in the switch. Configure an IP address for VLAN 10 and VLAN 20 below as the gateway of the PC below. Let me tell you about the process. The ARP we mentioned earlier, and the MAC address table we talked about today. This requires you to have a very godly understanding. Let's talk about it. How did it work? PC1 now wants to access PC2 across network segments. First it requests the MAC of its own gateway. It wants to send an ARP broadcast request. Send data to the switch. Tag 10 here. Then the switch is actually a fake router. Actually, the switch itself can handle. It's just that routers may be better understood by everyone. The switch itself will disassemble the data packet. After dismantling, you will see 3 layers. After seeing the 3rd floor, it is equivalent to entering the switch after typing the tag here. It will unpack itself. It will see 3 layers. The IP address requested by PC1. It is the IP address configured in this VLAN 10. Then the switch will reply to PC1. The switch is called backplane MAC. That is, there are no MACs under the interfaces of many switches. Only one backplane MAC. It's just a MAC address written on the back panel. For the entire switch. Reply to the PC with its MAC address. After the reply, the ARP is over. PC gets its MAC. Start data encapsulation. When it goes to request, the switch starts sending data directly to PC2. But the purpose of encapsulation MAC is the backplane MAC of the switch just replied. That is VLAN 10 MAC. Just send it. Switch to see the destination MAC is it. It depends on 3 layers. The 3rd layer you want to go is PC2. It checks the routing table. This is its direct connection. Wait a minute, we look at the routing table. It will display VLAN if 20. This is the next hop. For us now, the next hop to PC2 is VLAN if 20. This is a logical port. But everyone must pay attention. A logical port is, after all, a logical. The real data must be sent from the real physical interface. So which interface is it sent from? We will now go and send the ARP request. Request MAC for PC2. So which physical interface is this broadcast packet sent from? How to judge? At this time, the broadcast message. It will be sent from all interfaces that allow VLAN 20. For example, here is the switch below. There is an access interface. Belongs to VLAN 20. This interface also sends. There is a trunk interface. It passes VLAN 20. This interface also sends. All interfaces that allow VLAN 20 to pass through will be sent. Then send an ARP broadcast request. This is called VLAN if 20. In short, you will understand. Even if there are other interfaces are sent. But this data will definitely be sent to PC2. Because it belongs to VLAN 20. Then when PC2 receives this message, it's going to reply. It will reply its own MAC to this switch. Then the switch learns. Now the 01 interface corresponds to the MAC of PC2. It has an ARP table on itself. The record is IP and MAC. It now has a MAC address table on it. Record MAC and interface. So when the data is actually forwarded again, it knows to send out from this interface. What I said may be a little complicated. You must figure out its overall communication principle. That is to say, next hop is VLAN if 20. This is a virtual interface. What physical oral hair? All interfaces that allow VLAN 20 to pass. It's just that this broadcast packet is sent out. Only PC2 will reply. Because the request is its MAC. In ARP, target IP is PC2. Only PC2 replies. Once it's back, data flows through the interface of the switch. Will appear in its MAC address table. So the interface matches the MAC. Simultaneously, PC gets ARP reply. IP and MAC are also matched. Then the IP and MAC interfaces are all matched. Future access PC2. The switch knows that it is sent from the 0-1 interface. So, although the next hop you see in the routing table is a virtual interface, but actually for the switch, it can find the real physical outgoing interface. If you don't understand, you can take a look after class. It's normal to not understand the first time, but I've made it as clear as possible. Okay. Let's look at the configuration. We open this switch. First, let's look at the VLAN. Show VLAN brief. After coming in, we must still go under the interface. We just deleted the interface. Let's reconfigure. E00 interface. Switch port mode access. Then switch port mode access VLAN 10. Then we enter the E01 interface of the switch. The same. Switch port access VLAN 20. We have now divided the interface. Their configuration is exactly the same as before. Then we know how to enter the VLAN if interface of the switch. Also very simple. Interface VLAN 10. You'll see it here. The sub interface we entered just now is a sub. Now this is an if. This is a VLAN if the interface. After coming in, let's just configure the IP directly. This is VLAN 10. Just configure the gateway of VLAN 10. 192.168.10.254. 255.255.255.0. Then enter VLAN 20. Configure the address directly. 192.168.20.254. No shutdown. Let's now check the IP interface on the device now. You can see it here. 1 VLAN 10. 1 VLAN 20. VLAN 10 is 10.254. VLAN 20 is 20.254. So now the address is matched. Let's just look at the routing table. Show IP route. You will find, although it is a switch, but there is also routing table. We can see a directly connected network segment in the routing table. Is 10.0. This is VLAN 10. This is VLAN 20. So now you will find a data access 20.1 from PC1 to the switch here. It queries the routing table. It will see that PC1 wants to access 20. Then the local outgoing interface is VLAN 20. VLAN 20 is a virtual interface. Specifically why it can go out from the 0-1 interface in the end. Just follow the order I just said. It can eventually learn the interface. That is IP, MAC, and outgoing interface. It can be matched one by one through the local ARP table and MAC address table. Finally, the outbound interface can be found. Send traffic down. Let's do a test. From PC1 we now go to ping 20.1. I can still ping, although this picture has been changed. device delete to delete. But both of them have been able to communicate. That is, the above device can always help it forward data across network segments and VLANs. This is called mutual access between VLANs. Now many functions are integrated into this one device. And the real interface. Actually, it is an access interface. So actually, for the virtual interface in the device just now. That is, VLAN 10 and VLAN 20. When this data is received, it will be unpacked. When unpacking, it will remove the corresponding tag. When sending data in the future, it will put the 20 tag on it again. This is called repackaging. Then remove the 20 here. Everyone understands the specific concept of VLAN if. Okay. I will now make a summary with you. The purpose of our VLAN division. Not to block their flow. Actually, the main purpose is to make layer 2 unreachable between different VLANs. We just want it to be different on the second floor. Because the overall transmission method of the broadcast is the second layer. Layer 3 does not forward broadcasts. Router interface does not forward broadcasts. So strictly speaking, refers to the failure of the second floor. Instead of 3 layers. So we are more inclined to do traffic isolation for the second layer. And the broadcast is actually spread based on the LAN. Router interfaces do not forward broadcasts. Let me give you an example. If the router interface forwards the broadcast, the ARP packet we sent, if the router interface also forwards our billions of internet users around the world. Everyone sends broadcast packets every day. That's too exaggerated. Therefore, the router interface must not forward the broadcast. Only devices such as switches forward broadcast traffic. The purpose of our VLAN division is to make the second layer unreachable. Instead of 3 layers. What we finally achieved is to allow unicast. But the broadcast is not working. Normally there will still be some traffic exchange visits. Okay. I didn't expect to talk about VLAN for so long. It doesn't matter. We have a little configuration left for next class. Let's briefly introduce STP. In fact, it is biased for other configurations. Not so much to understand. So it's not hard to say. Most people will find STP difficult. But what we have learned at this stage is relatively simple. I will draw a picture first. This is a typical architecture diagram. Let's not talk about what STP is today. Let's first talk about what problem it solves. Let's draw a few devices first. Draw a few devices. This is a standard architecture diagram. These are switches. Assuming egress, this is a firewall. The devices below are all switches. This is the aggregation layer switch. Below is the access layer switch. Then the access layer is connected to the terminal. There are even PCs one by one below. So what are these devices at the access layer? Assuming this is the equipment in the office on the first floor. Behind this is the equipment in the office on the second floor. This is the equipment in the office on the third floor. Then, if such an environment. This is the operator. We are now going to data access. We are now on each floor. There is an access layer switch. Will be connected to the aggregation layer switch. This structure we talked about before. I won't describe it anymore. So think about what's wrong with this picture. These devices on the first floor are connected to the switch on the access layer on the first floor. The equipment on the second floor is connected to the switch on the second floor. The one on the third floor is connected to the switchboard on the third floor. Yeah. There is a single point of failure problem. The switch in the office on the second floor is connected to the aggregation layer. Only one line. If this thread breaks, we usually don't mean the line either. Usually refers to. For example, there is a problem with its interface or its interface. The interface is actually more prone to damage. But we usually say the line is broken. What we call a broken line. In fact, more refers to the interface has a problem. Once there is a problem with the line, then don't go online on the second floor now. Now connect to the external network with this one line. Generally speaking, the computer room has operation and maintenance. Someone will check regularly. Airtightness is also very strong. Let's talk about a single point of failure. Once this line is broken, the second floor will not be able to access the internet. And someone might have a way. If this thread breaks, just connect the 3 devices below. If it breaks later, the traffic on the second floor is like this. Do you think this is feasible? It won't work. Access layer switches usually have a performance problem. Even terminal. In the future, the lower layer terminal traffic will be aggregated from the upper connection port, sent to the upper aggregation layer device. On the whole, it has no way to withstand higher concurrent traffic at the same time. For example, this is a 48-port switch. Under normal circumstances, the traffic of the device below port 48 is sent upward. Suddenly it's broken. Then its traffic goes this way. And it suddenly wants to send more than 90 traffic. It may not be able to bear. This device simultaneously sends to the traffic all of a sudden. The device may be down. This is an access layer device. Access layer equipment is characterized by cheap. It doesn't perform well. So you can't connect like this. Let it go. Such a network is very bad. If you see a network like this on a person's project, it's definitely not okay to go to an interview like this. Even if you did that just now. What if there is a problem with this device? The 3 floors below will not be able to access the internet. So this is also called a single point of failure. This problem is very serious. So how to solve this problem? I deleted the above, because we are talking about STP today. In fact, there is no need to draw so many devices. Just to give you a feel for what it means, we can now add another device. Add a device at the aggregation layer. That is, I'm going to put another device here. After that I connect all the devices to it. They are actually connected. But I won't draw this one, because the NA stage cannot talk about this technology. In fact, there will be other technologies between them. Tell you later. After connecting, you will find, if this line is broken in the future, flow here. This thread is broken. Flow here. This thread is broken. Flow here. This is called multi-line multi-machine hot backup. So we pass some redundant lines and redundant equipment. Realize that a device is disconnected. Just leave this device. A line is broken. Traffic can still go this way. So it's a matter of backup. But this creates another problem. It can improve the reliability of the network. But it also creates problems. Let's take a look. We discussed switches today. For a broadcast packet, the switch, it's flooding. The incoming interface has received a broadcast data. Then it starts flooding. Received a data here. In addition to this receiving port, other ports are flooding. Flooding here. Here also flooding. Still flooding here. I'll be back here. It's just a line. Let's see if the other lines come back. Send this. It also came back. We just looked at the interface on the left. Actually there are other. Still from here. Still can come back. No matter how you go, you will come back. Don't look like it's covered. But they are not the same. Let's not discuss on the left now. Because the right side is actually sending out at the same time. No matter how this flow goes. All switches are flooding broadcast traffic. Then the switch sends a data packet. You will find it keeps charging. Everyone is sending it. These devices are also the same. Just this one broadcast message is sent here endlessly. This is the problem of packet flooding. It's called endless flooding. Always a broadcast packet. As long as a broadcast comes in, it will send nothing on the link until the final bandwidth is full. After that the device is down. After the bandwidth is full, the current performance of various hardware soars until the device goes down. Bandwidth is not the most important. Important is after it receives the broadcast message to deal with. Although the processing method is direct flooding, but also deal with. So the device will fail one day. This is called a broadcast storm. This is the first question. There is a second question. We just learned something called MAC address table. It stores the correspondence between the MAC address and the interface. For example, the MAC address of this host is A. This interface is 1. This interface is 2. This interface is 3. You will find, since a message was generated just now, because it has been receiving this broadcast packet, the source MAC of the broadcast packet is A. When data comes in, the MAC address table of the switch will record. Interface 1 corresponds to A. But when sent back, or this broadcast packet, the switch will record that interface 3 corresponds to A. In the same way, let's do another. Look. This data packet arrives at this switch from interface 2 again. The switch will record that interface 2 corresponds to A. So in this MAC address table, the storage is 1 corresponding to A. After a while, 2 corresponds to A. Then 3 corresponds to A. This is called the shock of the MAC address table, also known as MAC address table drift. It's all a very bad phenomenon. Our network is for normal business data forwarding. For example, a data is sent. Query MAC address table forwarding. Now in this MAC address table, for a while, A corresponds to 1. A while corresponds to 2. 1 will correspond to 3. Messages sent out in different periods. They are all sent from different interfaces. Amazing. This business cannot communicate normally. After the data is sent out, the host A cannot be found. So you'll find out now. This architecture creates 2 problems. A broadcast storm. One is MAC address drift. Both problems are difficult to solve. It will seriously interfere with our business. Before multi-line multi-machine hot backup, our business traffic forwarding is fine. It's nothing more than a bit of a single point of failure. Less stable business. But now even if the line is broken and redundant. But if the line continues, this problem can't be solved. Since we want to improve the reliability of the network, then it will bring some new problems in the network. We are now going to solve this new problem. We want to keep the network architecture like this. At the same time, new problems arising from the network architecture must be solved. Then we need new technology. There is a technology called Spanning Tree Protocol, called STP. Let's start with a brief introduction. For example, there is a loop. There is a broadcast storm. Then we can now do automatically block some interfaces. Everyday situation. This blocking is not to turn it off, but to mention one more thing. Logical blocking. This interface is open. But it does not forward business data. That is, this interface is not closed. When it sends data daily. Still receive. After we run STP. We'll send a message. Called BPDU message. If this message flows through this interface when sending. This interface can receive. And it also logs information locally. That is, it can receive messages. But it doesn't send messages. Under normal circumstances where our business is stable. It does not send any message. Secondly, this interface does not send business traffic. Any traffic that might loop these. It is not forwarded. So I can guarantee both. Under normal circumstances. This interface does not send data. It also ensures that if there is a problem with the other line, this interface can be automatically up. Then start forwarding. Like a button. If now in the network environment, there is a line forwarding, it can judge whether there is a loop in the network. If there is this port, block it. Blocking is not turning off. When it senses that other lines in the network have failed, then this interface is automatically up. Then start forwarding data traffic. This way it can be achieved without broadcast storm. No loop. It will not have MAC address drift. We can't talk more and more in depth in this class. The STP protocol is not commonly used now. It's not bad. Because it actually has to block some interfaces. Everyone should know. This interface is very expensive. Modules actually have overhead. You will find. If this link is not forwarded now. In fact, the other party's interface is wasted. It is equivalent to running an STP now. You will now find. There will be a problem with your device. This interface appears to be. But in fact it does not forward. It's wasted. So in fact, STP is a waste of network resources. So now STP is not very practical. But we still have to learn it. Because the algorithm of this protocol is quite powerful. STP is actually design some ports to be logically blocked. Then the port that is blocked usually does not forward traffic. But it will store some packet of configuration information in STP. Once it finds that there are no loops in the network, then the port will be up. Start forwarding data. This is the characteristic of this protocol. Let's talk about how it is implemented in the next class. Let's introduce STP first. STP can simulate an acyclic tree in the network. It will have a sequence problem. A tree must first have a root. Then the root of the tree is called the root bridge in STP. Bridge means switch. The root bridge is the root switch. As a core node of the entire STP. In an environment. Which device is the root device? Which device is the root bridge? We need to know how devices communicate. Let's take a look at the content of the courseware. For STP. You see there are 3 devices here. So among the 3 devices. Let's go first. Since we are going to build a tree. Where is the root of this tree? All 3 devices have the potential to be rooted. Then the choice of this root must have some parameter comparisons. Everyday devices can send some messages to each other. Comparison of size. It carries some parameters of the respective devices. Finally, a root device is elected through the election rules. Same. We also send messages. Select other things through some messages inside. This will be covered in the next lesson. We want to choose root bridge. Root port. Specified port. These 3 parameters. We have a message called a BPDU message. This is a message in STP. In this message, we'll carry all the parameters involved in the election. are comparable. The devices send messages to each other through. Then elect various roles. In the NA stage of STP, it is actually the election of roles. For STP, the difficulty lies in the election rules. This BPDU message is called Bridge Protocol Data Unit. It is responsible for a message that determines the status of all information roles in the entire STP. The entire STP protocol is actually carry out overall communication according to BPDU message, just like an OSPF hello packet. In fact, there are two kinds of BPDU. A configuration BPDU. One is called TCN. This we will talk about in the next class. But all its messages are called BPDU messages. You need to know this. A message for all status role determination. All role states are determined by such messages. Before we formally talk about the content of this message, let's first look at a few core parameters in it. In the next class we're going to do some data comparisons. These four are the first ones we will mention in the next lesson. In this lesson, let's briefly talk about. First, have a root ID. Root ID is the bridge ID of the root. BID is bridge ID. It's a little hard to understand. There are many STP parameters, and not easy to understand. But you must know. BPDU messages will be sent between devices in the future. For example, many devices in one environment. This is a switch, not a router. They both send BPDUs. Assuming now it is a root. But in the root ID of all switches. At that time, the device thought that the root would be filled in. For example, now the root is device 1. Then in the packets sent by all devices, root IDs are all 1. Both device 2 and device 3 send 1. Prove it now thinks this device is rooted. It also considers itself to be. Then send to the downstream equipment. It will also carry 1 in it. Also consider it root. STP relies on such BPDU messages to maintain the overall relationship. Root will always send to other devices. Other devices will keep sending. It's like picking a boss in an environment. The boss must always tell others that he is the boss. It has been notifying other devices that it is now acknowledging it. This is called BID. This parameter is always the root bridge ID. Let's talk about how to represent this ID in the next class. Let's talk about RPC again. This RPC is short for root pass cost. Refers to the distance from the device to the root. Then for the root. Root self to self overhead is 0. How to calculate other devices to root. In fact, it will also be related to the interface. In the next lesson we will talk about. First understand. Let's talk about bridge ID and port ID at the end. This message will be sent down. For example, now this message is sent to switch B. Then if it is the root, it should be filled like this. First root ID is yourself. That is, me. RPC is 0. Bridge ID or yourself. That is, me. Say this is interface 1. Port ID this is 1. This is the message it sent out. Arrived at switch B here. Switch B also needs to receive packets. And send it down. Then the message sent by switch B. The root ID is still the switch A. This parameter will not change. RPC will describe the distance from switch B to switch A here. After that, the bridge ID will be changed to itself. This is called your own bridge ID. In the whole STP, all devices are called bridges. So it describes itself. This port ID is its own. That is, an interface on switch B. If you received a rooted device, that includes routing to downstream devices. It is then sent to the downstream device. Certainly. It's blocked here. Let's not talk about the blocking problem. Assuming it was sent out. It received. Then all this inside is the route. This is the route path overhead sent to that device. Let's take switch B as an example. Let's understand briefly. Let's talk about the rest in the next class. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMO Education. I'm Grolin Annesley from ThinkMO. I hope today's content is helpful to you. See you next class. Bye classmates.